Hello, I'm Hyunyoung, and I'm going to present our work titled Fine-Grained Semantics Array Representation Enhancement for Self-Supervised Monocular Depth Estimation. The monocular depth estimation, also known as single image depth prediction, refers to the task of inferring depth maps of single images. This is an ill-posed problem in nature because a single image may have been produced from an infinite number of possible world scenes. Recently, as the neural networks have widely been used for various computer vision tasks, they are also adapted for monocular depth estimation. In the earlier stages, the networks were trained in a supervised way. This kind of method has been actively studied and shown great performance. However, there are several problems innate to the supervised depth prediction. It must require ground truth depth data, and this inevitably increases labeling cost and poses difficulty in gathering dense labels. Owing to such problems, the methods which don't require depth annotations are actively explored. This is referred to as unsupervised depth estimation. These methods only require unlabeled video clips without any annotations. They used consecutive video frames which are captured by a single moving camera for training. To train the depth network, the system requires an additional pose network to predict the depth and the relative camera poses between frames at the same time. Because the consecutive frames required for training are projections of the same 3D scene into different viewpoints. It means if we know the 3D model of the scene and the viewpoint of the camera at each video frame, we can create the corresponding images by geometric projection. Therefore, we need to first estimate the depth and pose using the networks from given image. Subsequently, we can synthesize images with the estimated depth and pose and compare the synthesized images with the original video frames to evaluate how precise the depth and pose predictions are. For this evaluation, the photometric loss, which computes the difference between the original image and the synthesized one, is mainly used. However, most of the works trained in this way suffer from limited supervision of photometric loss, especially in weak textured regions. For example, the recent works have large errors on textureless regions as shown in the figures. In addition, they cannot predict accurate object boundaries. These problems are also due to the moving objects and uncertainty in the pose network, which destabilize the training. Eventually, they lead to incorrect depth predictions, especially when training with only unlabeled video clips. In this study, we aim to improve self-supervised molecular depth estimation via the implicit use of semantic segmentation. The implicit use means we focus on optimizing the intermediate representations of depth networks instead of directly optimizing depth value itself. To this end, we propose two methods, the semantics-guided triple loss and the cross-test multi-embedding attention. The semantics-guided triple loss is the loss function to optimize depth representations by a kind of geometric guidance from scene semantics. The CMA module refines depth feature to produce more semantically consistent depth representations. In the end, our model eventually produces better depth predictions even in weak textured regions and at object boundaries. Next, we'll introduce our proposed methods. This is the overall architecture of the method. The depth network takes one image as input and outputs a per pixel depth map set T. The pose network receives concatenated two images and predicts relative camera pose between them. Then, we synthesize the target image by geometric projection and compute the photometric loss between the target image and the synthesized image to train both networks jointly. And then, we adopt a separate decoder for semantic segmentation. This network predicts segmentation map from input image. We train the semantic segmentation in a supervised way with the segmentation target. But for more practical usage, we don't use ground truth, but we generated pseudo-labels using the off-the-shelf segmentation network pre-trained on other datasets. Based on this multitasking architecture, the proposed semantics-guided triplet loss is applied. It optimizes the intermediate depth representations from each layer in the depth decoder. This loss function is computed by the geometric guidance from segmentation pseudo-labels. And the CMA module, located between each layer of two decoders, exchanges the feature representations from two heterogeneous tasks and refines the target representation. Now, Let me introduce the proposed semantics-guided triplet loss in detail. There is a local geometric relation from scene semantics. For example, adjacent pixels within each object have similar depth values, whereas those across semantic boundaries may have large depth differences. We apply this intuition through a metric learning problem. So first, we divide the semantic label into k by k size of image patches and select center of each patch as an anchor pixel. Then, we select the pixels that have the same class as that of the anchor as a positive set P+. The negative set has different class from that of the anchor pixel. And then, for each feature map from the layers of the depth decoder, we also divide these feature maps into the anchor, positive, and negative feature sets following the corresponding locations of the segmentation patches. By dividing the image into the overlapping patches, we can identify whether each patch crosses the boundary or not. The key insight here is that we aim to reduce the distance between the anchor and positive and increase the distance between the anchor and negatives. Therefore, we define positive and negative distance as the mean of the Euclidean distance between the anchor feature vector and each of positive and negative feature vectors. However, naively maximizing the negative distance as far as possible doesn't lead to our desired outcome, because the semantic border does not always guarantee that the depth of two separate objects should differ by a large amount. Instead, we adopt a triplet loss with a margin so that the distance is no longer optimized when the negative distance exceeds the positive distance more than a specific margin. This is the semantics-guided triplet loss we proposed. Next, let me introduce the CMA module. This module is located in the middle of each decoder layer and utilizes the information from the other decoder. It first computes cross-task similarity using each feature vector from two separate decoders. This similarity is computed as a dot product of the two heterogeneous feature vectors, and this value represents the quantitative amount of semantic representation that each depth feature refers to. We apply a linear projection to each of them respectively and compute the similarity in the embedding space. The cross-task similarity imposes large attention scores on specific depth features which are consistent with semantics. Inspired by multi-head attention from the transformer, we use multiple projection functions and independently compute the cross-task similarity through multiple subspaces. Then, we apply the softmax to attention scores from multiple embeddings. It means we measure the significance of results from each embedding on the corresponding attention scores. This is slightly different from the original multi-attention, where the results from each embedding head are concatenated and equally handled. Instead, we compute the importance of each embedding and we selectively exploit the outputs from multiple attentions. So far, I've just described one case of the CMA module that refines depth feature as the target. But in fact, we're using the two opposing CMA modules for one layer at the same time. It means the CMA module is a bidirectional architecture and it refines both depth and semantics features simultaneously. For the experiments, we used the Kitty dataset for training. This is an autonomous driving dataset for various computer vision tasks. For training semantic segmentation in a supervised way, we generated pseudo-labels using the pre-trained segmentation network, which was manually trained on the different dataset. In this table, we compare our method with recent studies about self-supervised molecular depth estimation. Some works are leveraging the information from semantics like ours, and some are not. Ours achieves the best results on the Kitty dataset and outperforms others in every metric. We also change our network backbone from Resonate 18 to Resonate 50. It shows the improvements, and ours with Resonate 50 still shows the best result. In this table, we evaluated the effectiveness of each proposed method. After applying each method, the semantics-guided triplet loss and the CMA module further improved the baseline respectively. The combination of both methods further boosts the performance. Both techniques are designed to refine the depth representation by leveraging semantic knowledge, and they showed synergistic improvements. It is also qualitatively demonstrated in the right figure. We also evaluated the semantic segmentation performance on the Kitty dataset. In this table, we focus more on how segmentation benefits from depth estimation through the CMA module rather than the final performance itself. So, the proposed CMA module also improved the segmentation performance, and the improvements are more clear when we used high-resolution images. As mentioned before, we designed the CMA module as a bidirectional architecture so that it also refines semantic features as a target with reference to depth representations. As a result, it leads to better segmentation performance. This table shows the effectiveness of the multi-embedding scheme of the CMA module. We varied the number of embedding functions and reported the results. This depth prediction performance improves as the number of embedding functions increases and shows the best result when it was 4. We also visualized the results in the figure below. The leftmost image is the prediction without the CMA module, and the number of embeddings increases as it goes to the right. It shows the more embeddings used, the more precise the object boundary, and the depth prediction becomes more aligned to semantics. This shows that the depth network can have more semantics-aware representations owing to the multi-embedding scheme. So, this is the conclusion. We designed the two methods towards a sharing purpose, semantics-aware representation enhancement. Therefore, the enhanced representation shows a synergistic performance boost, and it achieves the state-of-the-art result in the Kitty dataset. You can check our code in the link in the slide. Thank you for listening.